In this lesson, we are going to graph simple rational functions and use the graph of rational functions to solve real-life problems. A rational function is of the form f of x equals p of x over q of x, where p of x and q of x are polynomials, and our q of x value cannot be equal to 0, because we know that a denominator can't equal 0. So some examples of rational functions would be linear functions, quadratic functions, cubic functions, and etc. And I've written some examples here below in case you were having a hard time remembering what I was talking about. Now, a simple rational function is of the form y equals 1 over x, and that's going to be our parent function, and that is the graph of a hyperbola. Now, the hyperbola is a new term, but really what it is a graph that consists of two symmetrical branches, which we can see here. The parent function has two symmetrical branches in the first and third coordinates. The domain and range in these graphs are going to be all real numbers. And the only restrictions here is that they cannot be equal to 0. So our range is going to be all real numbers, but x can't equal 0. And we can see that in our y-axis because it will be our asymptote. So our vertical asymptote is where x equals 0. And our range will be all real numbers except for y can't equal 0. And you'll see that y equals 0 is our x-axis, which is our horizontal asymptote. Okay, so the function of the form y equals a over x, where a can't equal 0, has the same asymptotes, domain, and range as the parent function y equals 1 over x, but a is going to be our stretch in this case. So that won't affect the domain and range. What will affect the domain and range in this case will be our translations, or our h and k values that we've had in previous lessons. So in our new translations of the simple rational functions, we get y equals a over x minus h plus k. The new origin will be at hk, where the vertical asymptote will be at x equals h, because we don't want the denominator to be 0. So our vertical asymptote will be x equals h, and our horizontal asymptote will be at y equals k. Our first example says to graph y equals 3 over x minus 1 plus 2. State the domain and range. So the first thing we're going to do is notice that we have to find our domain and range. And we know that our domain means that we can't have 0 in the denominator. And if we have 1 for our x value, that would equal 0. So we know our domain is all real numbers except x can't equal 1. And the range will be all real numbers except y can't equal our k value, which is 2 in this case. So our vertical asymptote is going to be at the line x equals 1, and our horizontal asymptote will be at the line y equals 2. So we'll go ahead and plot our new hk, which will be our new origin. Remember, h is negative by default, so we have 1, 2. So there's our new origin, and our asymptotes on the line x equals 1 and y equals 2. Okay, so the next thing that we're going to do is notice, just as before, we've taken care of our h and k. So when we're going to plot points, we can just use the parent function 3 over x. And I'm going to pick 1. Now some of you are thinking, whoa, 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 x can't equal 1. That is true if we are going to plot points in our original function. But remember, we've already taken care of our shifts. So if I pick 1 now, we're actually going to be on the line x equals 2. So if I pick 1, plug it into the parent function, we get 3 over 1, which is 3. And if I pick the inverse, negative 1, I will get negative 3, right? And I'd like to pick numbers that are not going to give me fractions because it's going to be easier to graph. So another number would be good to pick would be 3 because that's just going to give me 1, and a negative 3 which will give me negative 1. So let's go ahead and plot those points. We have from our new origin 1, 3, and negative 1, negative 3, and 3, 1, and negative 3, negative 1. Now if you remember the image that we saw in the previous slides, we want to mimic, we only have 2 points, but we want to mimic the image of the hyperbola that we know that it's supposed to look like. 2 symmetrical branches that are going to swoop in and not touch either of the asymptotes. Notice we're not touching our asymptotes. We have 2 symmetrical branches, at least 2 points on each coordinate, so that will be the graph of our function. The next thing we want to look at will be another form that we're going to be graphing, and that is y equals ax plus b over cx plus d. And an example of this might be y equals 3x plus 6 over 4x minus 7. Just an example. So, if we want to find the vertical asymptote, notice that we don't have the parent function form anymore. This does not look like a over x minus h plus k. So we have to find new values, right? So I need my mouse. If we look at the vertical asymptote of this form, we want the value where x makes the denominator 0. So what we're going to do is we're actually going to solve the denominator for 0 for x. So if we solve this equation, set it equal to 0 and solve for x, we get x equals negative d over c. So this would be our new vertical asymptote for this form of the graph. And that would give us the domain of all real numbers, but x cannot equal negative d over c. And in this case, it would be positive 7 over 4 would be our vertical asymptote. And similarly, in the horizontal asymptote, we want a value that occurs at the line y equals a over c. So our range would be all real numbers except y cannot equal a over c. And in this case, a over c would be 3/4. So if we do an example of this form, we have y equals x minus 2 over 3x plus 3. So the first thing we want to do is find our domain, which we know is setting the denominator equal to 0 and finding x. So 3x plus 3 equals 0 will give us an x value of negative 1. So our domain is going to be all real numbers except x can't equal negative 1. And our vertical asymptote, we'll note, is going to be x equals negative 1. The range, remember, is our a over c value, which in this case equals 1/3. So the range is going to be all real numbers except y cannot equal 1/3. And we'll note that our horizontal asymptote is going to be at y equals 1/3. So we can go ahead and plot those. X is negative 1 for our asymptotes for our graph. And with this pen it's a little tricky, but I'm going to do my very best. Y equals 1/3. Okay, so the next thing that we want to do is again plot some points. But this time we're not going to have a fancy parent function to go to, so we're just going to have to wing it. The one thing that I do urge you to do is to choose at least 2 points on either side of the vertical asymptote so that we know where our coordinates are lying and we know where our graph should be plotted without just guessing. So from our original asymptote, because we aren't exactly sure where our asymptote or our origin lies in our new asymptotes here, so we're going to go from our original asymptote of 0, 0. and pick some new x values that will give us points on either side of the asymptote. So I picked -2, which is going to be right about here. And I also picked -4. So we have 2 points on this side of the asymptote. And I picked 1 and 3, so we have 2 points on this side of the asymptote. So plugging this into our original equation will give us -4 over -3, which is 4/3. Plugging -4 in, we'll get -6 over -9, which will give us 2/3. Plugging 1 in, we'll get -1/6, and plugging 3 in, we'll get a +1/6. So if we plot those points from the original origin, we have -2 4/3, which is about 1 1/3, -4 and 2/3, which is right about there. Okay, and plugging 1 in from the original origin, -1/6, and 3, +1/6, which note is still below the asymptote because 1/6 is less than 1/3. And we now have 2 points in 2 different coordinates opposite each other, so we know that we're going to get 2 symmetrical branches. But this function is just going to be a reflection of the parent function, so we're going to have our branches in the second and fourth coordinate instead. Notice as you approach infinity, the graph is going to approach the a over c line, which is a limit, and you'll learn more about that in calculus. Okay, so our last example is going to be a modeling example, and it says, a senior class is sponsoring a dinner. The cost of catering of the dinner is $9.95 per person plus an $18 delivery charge. So it says write a model that gives the average cost per person. So first what we want to do is classify our variables. I'm going to use A for the average cost. I am going to note that 18 is our delivery charge. I'm going to note that our unit cost is $9.95 per person, and our number of people will give the variable of p. Okay? So if we put that into a model, we're going to get A for the average is equal to 18, which is our delivery charge, plus $9.95 per person, all divided by the number of people for the average. So the next thing it asks us to do is to graph the model. We'll want to notice that this can actually be written as 18 over p plus 995 over p times p. So we can cancel those out. So you can choose to write it either way. This is just fine. But if you write it in this method, it will look very similar to what we just graphed in this lesson, where our 995 is our k value, and we have no vertical asymptote h. So p is actually our x here, and our a is our y. So our vertical asymptote is going to be at x equals 0 because we can't have negative people. And our horizontal asymptote is going to be at our 995, which is our rate per person. So if we plot some points here first, 10, oops, that's 12, 16, 20, 2, 4, 6, oops, 8, 10, 12, 14. All right, let's start that over. Stop talking while I'm writing and I'll make more sense. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 at the top. Perfect. And For the bottom, I'm probably going to go by 5s, so we'll have 25. Perfect. So again, our vertical asymptote is going to be at x equals 0 because we can't have negative people. And our horizontal asymptote is going to be at 95, which is our k value. So that's going to be around here. So we'll know that when we're graphing, we should try and stay above this line because if it isn't, we're probably going in the wrong direction. So picking some points, we already denoted our k value. So when we pick our x and y values, which will be actually our p and a values, I'm going to choose values that 18 is divisible by so that we don't end up with fractions. So if I picked 1, 18 divided by 1 is just 18, plus approximately 10 will give us 28. So that will be at 128, somewhere way up here. Again, let's pick 3 because we know we can divide 18 by 3, 6, 9, and 18. If we plug those numbers in, we'll get close to 16, close to 13, close to 12, and close to 11. Plotting those points, 3, 16, 6, 13, 9, and 12, and 18, and 11. So notice that we still have a section of the hyperbola, but because we don't want negative people or negative dollars, we won't go in the other coordinates. Now the next part of our question asks, estimate the number of people needed to lower the cost to $11 per person. So if we want to estimate at 11, which will be our average, somewhere close to here, and the graph is going to show us that it's past 15, but not quite to 18. So I'm going to estimate that we will need approximately 17 people to lower the cost to $11 per person, or to raise it to lower it to $11 per person. That is including the fee. And the last question asks us, describe what happens to the average cost per person as the number increases. So notice when we picked our points, as we increase the number of people, we're getting closer and closer to that $9.95. So that would be the answer. As we increase the average cost per person increases, we get closer and closer to $9.95. So a quick review here. The rational function, remember, is y equals, or f of x equals, p of x over q of x, where p of x and q of x are polynomials. Q of x can't be equal to 0. The hyperbola is the parent function y equals 1 over x, or y equals a over x, where a is the stretch and that can't equal 0. And the hyperbola is the two symmetrical parts with the points of pairs xy and negative x, negative y. Other forms that we learned about today are the y equals a over x minus h plus k, where our h and k are our shifts and also our asymptotes, and y equals ax plus b over cx plus d, where our horizontal asymptote is our a over c, y line, and our vertical is where the x makes the denominator equal to 0. And that will conclude the lesson.